Okay, welcome back for the last session this week, and just talking to Ivan about the rest of the course. We're going to finish next week. So next week I will finish a little bit. I think I'll have a little bit to finish off on photovoltaics, but then I'll talk briefly about some of the issues of storage and system integration. It'll be fairly brief because we don't have a lot of time left. Okay, so we got to further on than this slide here yesterday, but I just wanted to recap on the idea of the band gap. And the band gap is a term that refers to the energy required to move electrons into the conduction band. And that has a very big impact on the way in which photovoltaics operate, because if you look at the various materials, and I'm now at the slide that I finished on yesterday, if you look at the various materials here, you can see the magnitude of the band gap. And silicon has a relatively small band gap, which together with the fact that it is a very common element on the Earth, is one of the reasons, or two of the reasons, why it's used extensively for photovoltaic system. And the significance of it is that if we look at the spectrum of the radiation versus wavelength, then the fact that there is a finite amount of energy required to move the electrons into the conduction band means that there's a range of wavelengths that a particular PV technology cannot use. So if the band gap for silicon, that actually corresponds to a wavelength of 1.12 micrometers. And so all the available energy in the solar radiation above that wavelength is not available to that technology. And it also means that when we go down in wavelength, it's only the part of the spectrum that's under the dashed line that is actually useful to dislodging the electrons, because the excess energy doesn't serve any purpose. That excess energy effectively goes into thermal energy of the semiconductor material, which what engineers know as heat. And that's one of the reasons why photovoltaic technologies usually produce more heat than they produce electricity. Remember, we saw efficiency figures for different types of photovoltaic materials, and we're looking at numbers that are certainly less than 20%. So what happens is that of the incident energy onto the PV module, most of that energy ends up as heat. And one of the big areas in photovoltaics research, not so much commercialized as yet, is trying to develop ways in which that excess heat can be removed from the back of a PV module and used to do things like run air conditioning systems or heat a building or some other application like that. And the advantage of those, what are called PV thermal systems, PVT systems, is that if you take heat away from the module, you lower the cell temperature. And as we'll see, lowering the cell temperature improves the efficiency of the PV system. So this curve here shows a typical situation for a silicon PV cell, where the darker grey area down here is the energy that cell can convert into electricity, because the energy above that and in the right frequency band, or the right wavelength band, goes into producing heat, and the energy at the higher wavelengths is just not available to that particular technology. So you can probably get a sense from this why multi-layer technologies work. Okay, we saw from the famous NREL chart yesterday that the very high or relatively high efficiency PV technologies are the ones that have multiple layers in the PV cell. And what those multiple layers do is actually work on different bands of wavelength. So if we could combine a silicon layer with a layer of another material that could accept higher wavelengths, then clearly we're likely to get an improvement in efficiency. The real crunch, of course, from the commercial reality of it is, can you do that sufficiently cheaply that the final price of the electricity, the lifetime cost of the electricity, is sufficiently low? And as far as I know, up to now, the answer to that question is no. But like I said yesterday, I expect that situation to change substantially in the not too distant future. Okay, so of the common technologies that are used on commercial PV systems, they are split into four main categories. There's monocrystalline silicon, where the solar cell, and a solar cell is typically about 10 centimeters square. I forgot to give you that information. So that's a basic unit of a PV module. That cell would be made out of a single crystal of silicon. It has the highest efficiency of commercial PV technologies, but relatively speaking, more complex manufacturing and a greater temperature sensitivity, which basically means that its decrease in efficiency as the temperature increases is greater than the other technologies that you see here. Multicrystalline or polysilicon are cheaper, less efficient, cheaper to manufacture. Amorphous silicon, which is usually called thin film technology, is cheaper still, but it also has the lowest efficiency. So again, you can see the relationship in a general form between the efficiency of the technology and the cost of it. Okay, so if you want the cheapest possible PV technology, then you go to thin film technology, but you're forced to use a technology that may not be much more than 10% efficient. The newer types of thin film technologies use other material like cadmium telluride. I don't know very much about these technologies. I do know that they haven't as yet made a big impact on the commercial PV scene, but here you see some of the advantages. It's claimed to be cheaper than the other silicon thin film technologies with a smaller temperature sensitivity. So again, we have a situation where no one technology is obviously better than any other technology. It's going to come down to maybe there are situations when the high efficiency is important. You know, maybe if you're going to put a PV system on the roof of a building, then you're limited in space. And so to get the maximum power output from that, you could choose a higher efficiency module, even if it is more expensive. Okay, I'll just briefly go through some of the manufacturing processes for PV systems, because I want to give you here a balance with what I've said when we were talking about wind turbines. I talked a lot about the problems of disposing of wind turbine blades when a wind turbine has finished its operational life. There are similar problems with PV systems as well. And you can read in the research literature and other places. I talked briefly about this during the first lecture, that people are anticipating a significant problem in the next 20 or 30 years with the large amount measured in tons, millions of tons of PV technology that needs to be recycled in some sort of way. So silicon starts out usually as sand. Okay, it's an abundant material, which is, as I said before, one of the reasons that it is used. And then you can see quite a number of fairly sophisticated and probably environmentally potentially dangerous, at least when you've got hydrogen chloride or hydrochloric acid and hydrogen being used to produce the high purity polysilicon that is used for a range of applications. One thing that I haven't mentioned is that a PV cell is actually a semiconductor. So it's very much related to semiconductors that are used for chips in computers and other uses like that. It's possible to get away with a lower quality silicon product that is used, as they call solar grade, used for PV modules. Okay, so for the silicon process, there's basically two ways. Either a monocrystalline wafer is produced or a polycrystalline wafer. And a wafer, if you're not familiar with the term, just means a very thin sheet of silicon. So a thin sheet of silicon that will be about 10 centimeters by 10 centimeters, and that is going to be the basis of a PV cell. And you can see here the ways in which the different technologies are produced from silicon to get the monocrystalline and then the polycrystalline alternatives, as you can see there. And then once we do that, there's further analysis that will end up either as a standard crystalline module, a concentrating module, or a thin film module. The purpose of showing you these slides is not to go through the manufacturing process in detail, but just to give you a sense of what is behind the issues that we're going to be looking at in the next few slides about recyclability and sustainability of the technology. Okay, there's quite a lot of information in the literature talking about the sustainability and the recyclability of photovoltaic systems. And you can see here, for example, the information that looks at how much photovoltaic waste there is going to be. And this particular one predicts that by 2050, I may not see it, but you very likely will see that that year. There's going to be something like 100 million tons of waste, what would otherwise be waste photovoltaic systems. And a lot of people are advocating at the moment that now is the time that we need to start setting up for the recycling of these components, because the later you leave it, the more difficult it is going to be. And you might like to think what sort of policies, government laws or rules for purchasing photovoltaic systems could lead or could improve the recyclability of them. So just to give you, again, a little bit more information about a PV system, it usually has what I would call as an Australian, an aluminium frame, what they call in North America an aluminum frame, which holds the whole module together. And underneath that, there is a glass cover. And that glass cover has the role of protecting the PV cells. So, for example, from hail damage, if there's hail or other sorts of damage like that, there is a slight disadvantage in having a glass cover, because any glass cover can cause a greenhouse effect. That the longer length radiation that isn't absorbed by the PV modules and gets reflected actually gets trapped by the glass. So the glass can have an adverse effect on the module or the cell temperature. But the frame and the glass, they're relatively easy things to recycle. The problem with PV is more that is more the problem of how you collect and process the modules. It's not the actual chemical and other components of the module that is the problem. The problem is, even if you have a city like Novosibirsk and you are wanting to collect expired PV modules from around the city, that can be a major issue just in the collection of them. So there's the frame to hold it together. There's adhesive that does that job. Then there is the glass, and then there's what they call an encapsulation film. And the encapsulation film is again there to protect the solar cells that you see below that. And on the backside of the module, there's further protection that is required to maintain its integrity. And here you can see a expanded view of this part of the module here. Here you see 4 PV cells. Okay, so each one of those nearly square grey squares there is a PV cell. And the fact that the squares are cut at the edge, at the corners, probably means that it's a monocrystalline cell, because the single crystal is usually grown in a cylindrical form. And so when it is cut, trimming the corners like that get you a bigger outcome for your cell from a particular diameter of the manufacturing. And then the electrical contacts go through there with the tabbing, and the bus bar is underneath. And here is a list of some of the processes that are involved in the manufacturing of PV cells, again, showing you the complexity of it. Here on the right-hand top side is a list of the various components, and they differ significantly depending on whether it's a thin film module or a conventional module. But glass is obviously important, and that's fortunately because that is, along with the aluminum, they're the most easily recyclable parts of the module. Then you have plastic, silicons, and other metal that are potentially recyclable, but it is difficult to do that. So if you're interested in that issue, you can look at the full paper that I took the front page from on the previous slide, and both these figures come from that paper, and you can learn a lot more about the reality of actually doing these jobs. It would be nice to ensure that PV modules can be recycled, just as it would be nice to ensure that wind turbine blades can be recycled, but it's a difficult thing to do. Okay, in terms of cost, as you would expect, the solar cells themselves are the main component of the cost. And after that, the aluminum frame is surprisingly the next most costly part of it. And there are PV modules appearing on the market that don't have a frame. And that, I imagine, that is there so that it can reduce the cost. Okay, now just a little bit of terminology. This is a fairly old slide, but it shows the right terms. So I've talked about a PV cell. That is a single unit in a PV module. Then we have a PV module, and that PV module is a collection of cells. The largest PV modules that are available at the moment, and I'll give you an example of that later in the lecture, they will have 72 cells in them. This one is 1, 2, 3, 4, 5, 6, 2, 4, 6, 8, 10, 12. This is a 72. Oh, no, did I count that right? 2, 4, 6 along the top, 2, 4, 6, 8, 10, 12, 6, yeah, that's a 72 cell module as well. I was surprised at that because this is a fairly old cell, and I thought 72 cell modules were relatively recent. So we have a PV cell that in conjunction with other PV cells makes up a module. Then that module may be connected with other modules in what's called a string. And usually speaking, a string is a collection of PV modules that are wired in series. Not always, but generally. And then those modules make up an array. And an array can be relatively small if it's on a residential building. It can be a medium-sized one on a factory, or it can be a huge one on a PV farm, as you can see here. Okay. In order to get a better idea of how a PV cell operates, it's important to at least have a look at the equivalent circuit for a PV cell. So basically what we have is an NP junction here. We have the metal collector up the top here, which gives us the voltage difference and the load on the right. And the equivalent circuit is shown down the bottom here. We have a cell resistance. We have what's called a shunt resistance. And here is the diode, which is in effect the representation of the PN junction. And here on the extreme left here, we have the current that is induced by the photoelectric effect as the sunlight falls upon the PN junction and causes the electrons to move. The basic equation for the current that is produced is this equation here. Which is a useful equation if you're going to do something like write a MATLAB code in order to determine how a PV cell works. But in practice, it doesn't have a lot of value because we get the information effectively from the manufacturer specifications. And I'll show you at the end of the lecture, if we use SAM to do a PV system modeling, then SAM's database has the information of which this equation is the approximation to. But that gives you a little bit of an idea of how the current and the voltage that is generated by the photoelectric effect acting on the PV cell actually interact with each other. Okay, the other thing to note is that in a PV module, the cells are always connected in series. Okay, so you can see the dark black line that is running down through the first column of cells and then coming up through the second column of cells. That is the electrical connection that gives the series connection for all the cells. The typical voltage output from a PV cell is 0.6 of a volt or less. Okay, so in order to get a meaningful voltage, they have to be connected in series. This is basically this series connection is also the reason why shading is such a problem for a PV system, because as I will show you, I think it's in the next lecture that I'll get onto on Tuesday. If, for example, if you could shade just one of those cells and one cell only, you would stop the whole module from working. Okay, so that's the reason, or that's the reason behind the statement that I've made a couple of times already, that the effect on the power output of shading a certain percentage of a PV array is much, much greater than the percentage that is shaded. Okay, So here are some basic fundamentals of a PV system. For a particular level of solar radiation and a particular cell temperature, if we plot the current versus the voltage that is coming out of a PV system, so we're looking at the current and the voltage at the output here, then it is given by the IV curve that you see here. SC stands for short circuit. So this is the short circuit current in the cell, and the short circuit current is the maximum current that cell can have. And if we go down to the x-axis, we see the open circuit voltage. And the open circuit voltage is the maximum voltage that the cell will produce. And typically, 0.6 of a volt for the open circuit voltage. The short circuit current, typically 2.75 amps. These are probably a little bit old, these numbers, but they won't be too far wrong. Now, from this IV curve, you can see two things. One, the IV curve fits within the rectangle that's defined by the short circuit current and the open circuit voltage. And that can be important information. If you turn the IV curve into a power curve, and power is simply I times the voltage, then a PV cell will have a power curve that looks like that. And where you want to be operating is at this point here, because this point here, MP stands for maximum power, is obviously the point that is giving you that maximum power. So this is a little bit like what happens with wind turbines when you have the power coefficient versus tip speed ratio reaches a maximum at the maximum power point. It's a very, very similar situation for PV, except that maximum power point, that is usually a sharper peak for photovoltaics than it is for wind turbines. But if you look then at the two main ways in which the values and the shape of these curves are changed, the cell temperature, you can see for different cell temperatures, 60 degrees is not an unusual cell temperature, particularly for a desert application. Okay. Fortunately, in cold climates like we have and like you have, we get more of our operation down the lower temperature regions, and there's actually more power in a PV system in cold weather. And of course, the solar radiation or irradiance has a huge effect on that. And so if the irradiation changes, then the maximum power point changes. And so if a cloud goes over the sun or partially covers the sun, then the power curve changes, and the control system for in the inverter has to be able to maintain that maximum power point. And it usually has to do it without knowing what the irradiance is. So it's a little bit like the problem with wind turbines, where you have to keep a constant tip speed ratio, even when you don't know what the wind speed is going to be. And that's why the reason for what I've said a couple of times, that the way you do maximum power point tracking for a PV system is actually very similar to what you do for a wind turbine. Okay, and just some very basic electronics. I've mentioned already I teach this material to mechanical engineers. They sometimes struggle with the idea of which of these two is in series and which is in parallel. In the class for the mechanical engineering students, I often ask them which is which, and a good proportion of them get it wrong. But I would expect you people to be one up on that, because if you have a system in parallel, then you add the currents. I think I've got that right. Yes, I'm a mechanical engineer as well, so I always have to stop and think about that. Okay, what I'm going to do now is take you through the manufacturer's specification sheet for a typical PV module. There's nothing particularly special about this manufacturer, and I'm not an agent for that manufacturer, so I don't have any financial benefit in giving you this information. I've chosen it because it is typical of current PV modules, and that's the only reason that I've done that. So this is a 335 watt module. So just like a wind turbine nameplate capacity or rated power is the maximum power that a wind turbine can produce, it's the same for a PV module. This is the amount, of power that would be produced if the module is irradiated at 1 kilowatt per square meter and the cell temperature is 25 degrees. Okay, so this is a high efficiency module, and it's, as you would expect, a monocrystalline 17%, which is pretty impressive. It has a positive tolerance. Now, I bet that nobody listening to me actually has any idea of what that means. This statement here of a positive tolerance. What it means, you can begin to appreciate if you look at the information that you see in the top left-hand corner. This is nominally, nominally a 335 watt module, but in fact, it comes in 3 varieties. There's a 335, a 330, and a 325 version of this module. Those numbers there relate to the rated power of that module. And the variation in the rated power comes about because even though the manufacture of silicon cells is very tightly controlled, and as we've seen, it's a little bit like the manufacture of semiconductors for computer chips and things like that, you still get variations in the quality of the module. So what most of the manufacturers do is that every time a new module is made, it goes under what's called a flash test. The manufacturer has a special compartment that the module is placed in, and then a lamp is irradiated at 1 kilowatt per square meter, aiming at the module. Now, this is done for about a millisecond, okay, because PV has no inertia. You don't have to illuminate a module for very long before you can measure the power output. So that flash test is used by all the good manufacturers of PV modules to test every module that they manufacture. And so for this module here, they do the flash test, and then they decide which of these categories the newly made module fits into. So if the flash test says it's 327 watts output, then it will be classified as a 325 watt module. And that's where they get the idea of positive tolerance, that the peak power of the module is actually going to be more than what is specified in that number there. All modules are tested for extreme conditions. Wind and snow and hail are the main extreme conditions. There is a problem that is called potential induced degradation, which often happens more when a module is installed in a hot climate, like in a desert. And that can be a combination of leaking of ions to and from the cell, and that has the effect of increasing the shunt resistance in the electric model for a PV cell. And the other two things here are not particularly important. There's a little bit of information about what they do that they claim is special. The last piece of information that you need to be aware of on the first page is the warranty or the guarantee. Now, this is the area where photovoltaics has a huge advantage, because photovoltaics involves no moving parts. There's no gearboxes and there's no generators to fail. And most PV manufacturers will give a guarantee on their product for 20 or 25 years, which is pretty fantastic. I mean, I'd love to be able to buy a car that had a 20-year guarantee. And that guarantee consists of a statement about how much power the module will produce after that time compared to the rated power when you first buy it. All modules degrade over time, and typically they degrade over 20 years by something like 20%. So after 20 years, you would expect this particular module to produce a peak power of 265 watts, about 70 watts less than what it is shown here. Okay, so that's, when you think about it in total, that's a pretty big drop, but the yearly drop or the rate of change of the cell efficiency is quite small. And one of the interesting things about this warranty on the PV modules itself is that it has inspired the power electronics manufacturers to give similar warranties on their products. And they actually, I think, have a harder job of doing that. Okay, so here's a run through the specifications of the PV module. So you can see here the 3 columns represent the 3 divisions that we talked about from looking at the front page of this spec sheets. Here is the module operating range. You can see that it can go up to temperatures of 85 degrees. And in the next table here, you see what's called the performance for the nominal operating cell temperature, NOCT, because the flash test is done at 25 degrees. And because the flash test lasts only for a millisecond or so, it's not going to heat up the module. Okay, and you can imagine, the temperature in the factory where the modules are made is probably somewhere in the low 20s anyway. So 25 degrees is a pretty good temperature for the module. However, in reality, the cell temperatures are significantly higher than that. So there's a condition called the nominal operating cell temperature, which is given here, is 45 degrees. Okay, so that would correspond to an ambient temperature probably in the low 30s. So probably in Calgary, that would not occur very often in summer, but it does occur. And the performance of a PV module at the nominal operating cell temperature is significantly less than it is at the rated conditions, at the standard conditions. Okay, and that is due to the fact that virtually all PV technologies get less efficient as the temperature increases. And in this table here, the next 3 entries after that cell temperature are actually the most important pieces of information on this spec sheet. It tells you how much the efficiency drops off with the temperature. So here, 0.41% per degree centigrade. Okay, that's pretty substantial. So if you have a climate like ours, where you can go from, say, -30 to +40, that's a huge variation in efficiency. I remember a number of years ago, I went to a presentation where a graduate student was talking about his project was to monitor the performance of a PV system right in the north of Canada, right well past the Arctic Circle. And they were getting efficiencies on that system of something like 20% greater than the manufacturer specifications on a sheet like this, all due to the much lower operating temperatures that you get there. So here's the type of the cell and its dimensions. So it's about 15 centimeters by 15 centimeters. There's 72 of them. And this particular module, 335 watts, is a large, physically large module that would be designed for a solar farm rather than home installation. Modules that are designed for home installation will usually have about 60 cells in them. So the weight is 25 kilograms. You know, that's pretty heavy if you've got to lift that up onto a roof of a house to install it. Then there's just a little bit of information about the details of it. And over here is the information, the same information that I showed on this slide. Okay, the IV curve and the PV curve as a function of temperature and irradiance. And you can see that the actual information for this commercial PV system is very similar to what I was showing you before. A little bit hard to see on the screen. If you want to look at it in more detail, you can have a look at the PowerPoint, blow up the PowerPoint and have a look at it more closely. So this data sheet here, or specifications, every PV manufacturer produces that for their PV modules. And like I said, usually one of the most important things that you need to look for is the temperature coefficient for the efficiency or the maximum power point. Okay. I've talked a little bit about the various types of inverters because we've had now enough of a look at how the basic physics of a PV system works in order to produce the power when it's irradiated by the sun. What I want to talk about in conjunction with this table here about inverters is some of the other features of the different types of inverters. I've talked about the prices. Okay. What you see here is some very important information. If we have a string inverter, that is an inverter that is handling maybe 5 or maybe 10 or maybe even more PV modules, then it actually has poor performance if there's shading. And the next lecture that I give you will show you exactly why that's happening, because the next lecture is all about shading. If we do a DC power optimizer, in other words, we don't invert the electricity that's produced by every module, but we have a DC optimizer that does the maximum power point tracking, that is more efficient. And even more efficient still is a microinverter. And if you remember from the table that we looked at yesterday, the trend in efficiency is opposite the trend in cost. That usually a string inverter is cheaper than a power optimizer, which is cheaper than a microinverter. This can be important because there's clearly a trade-off between cost and possible response to shading. And often for PV systems in cities, shading is an important issue. I talked yesterday about a lamppost shading one of our systems on the University of Calgary campus. But if you build any system in a city, you run the risk of having it shaded at some point of its operation. And particularly if you remember that you're designing or installing a system that you want to have operating for 20 or 25 years. You know, and in that time, your next door neighbor might build a bigger house and, you know, either cut off your sunshine or cause shading. So shading can be a really important issue for some PV systems. When you set up a solar farm, then it's usually not an issue at all, except to the extent that one row of a PV module, and I'll no, I won't go back to the start. It's on the previous slide. If you have a look, I meant to point this out. The photo of the PV system that I showed at the start of the lecture yesterday, that shows the shade from one row of modules just about to touch the bottom of the row behind it. So you do get a little bit of what's called self-shading on a PV farm, but you very rarely get any other form of shading. You'll never see a PV farm with trees around it, okay, because trees obviously cause significant shading. And so also too, if you're going to install a PV system on a roof, you often have less control over the inclination and the tilt angle and the azimuth angle. And again, the variation in the different types of inverters follows that. The other thing that is very interesting is that if you have a string inverter, you don't necessarily get any detailed information about the individual modules. If you have a power optimizer or a microinverter, then those devices can allow broadcasting to the web of the performance of the module that it's connected to. And I'm not sure whether I'll have time for this, but I do have a lecture on monitoring of PV systems. And that lecture shows how you can use information about the performance of the individual modules to tell if there's a problem with the module. And sometimes you can also tell if there's a problem with the inverter. This is an issue that I haven't said much about, but we now have enough information to talk about it. I was talking about the natural variation that you get in the performance of individual modules. Okay, so even if I am buying modules for a solar farm, for example, I probably would go for the highest power output ones, although they would be the most expensive ones. But even within one of these classes of module, there's going to be variations. Okay, so one of these modules might produce 337 watts, another might produce 341 watts or something like that. And what that leads to is the idea of module mismatch. If you have two modules that are connected to a single inverter, and one of the modules has a different maximum power point to the other module, then the inverter will cause mismatch. You won't get the maximum amount of power out of both modules. And clearly that is a problem when you have a string inverter, but it's not a problem if you have a microinverter. And then, of course, clear number of electronic components correlates directly with the cost of the various options. And we know now that the string inverter is the cheapest, the optimizer the next, and the microinverter as well. And of course, safety can be an issue as well. One of the reasons for DC optimizers and microinverters for small scale system is that they remove the need for high voltage DC connections. And that can be a safety issue as well. So we've seen with the choice of inverters that there's a whole range of possibilities. And we've seen how those different ways of doing it, from string inverters to microinverters, how that impacts on cost. And we've seen here how that can impact on system performance. So what does a DC optimizer look like? There you go there. It's about the size of an external hard drive. And as you can see, it's pretty much the same color. Okay, they're very small. Even a microinverter would be something like 15 by 25 centimeters and probably about 2 or 3 centimeters thick. They're quite small. Okay, so that, I think, is the end of that lecture. What I wanted to do now is just very quickly take you through SAM to show you to show you how SAM provides a lot of the information about the performance of PV modules that I've just talked about in this lecture. So I'm just waiting for SAM to fire up, and then it's coming up now. So I should be now able to share the screen. No idea what that means. Okay, I seem to have a number of different SAM processes going. So I'll try and kill a number of those so I make sure that I share the one that I'm actually using. Okay, so I should be able to share, where are we? Here. Should be able to share that one. Okay, so now you should be able to see the front end of the SAM module. So I'm going to start a new project. I'm going to look at photovoltaics, look at a detailed PV module. You can, what I'm going to encourage you to do is try playing around with SAM yourself, because it's free and it's relatively easy to find your way around it. So let's say we go to a detailed photovoltaic module. I'm not going to do any lifetime cost of electricity calculations, so no financial model. And we come to the specification of the solar resource. Again, I'm not going to spend any time worrying about that because I haven't yet still been able to do it for novice birth. So maybe someone in the audience will be able to do that for us. But let me go to the module itself and take just an example module from the large number that are stored in the database. Now, again, there's nothing special about this particular module. Okay, it is just one of the many that's in the SAM database. And if you look at the information here, which I will scroll up, you'll see pretty much the same sort of information that we saw on the manufacturer's spec sheet. Here is the current versus voltage curve for the module. So the open circuit voltage for the module is close to 70 volts. This is a very efficient module. This is about 21% efficient, and the temperature coefficient is less than the module that we saw before. So this has better temperature behavior. This is something that I haven't told you about. This is if the module is bifacial. And a bifacial module is one that has the PV cells on both sides of the module. I didn't make a very big deal of it when I was showing you the glass and the aluminium frame for a PV module, but a standard PV module has an opaque backing at the back of the module. A bifacial module doesn't have that. It has an extra layer of solar cells at the back, and that allows the module to capture the sunlight that is reflected from the ground. And it's actually a very popular technology in Canada because ground reflection tends to be greater in wintertime when there's snow on the ground. Okay, because reflection off snow is usually much more than reflection off grass and dirt and things like that. So many of the latest installations in Canada are actually bifacial installations. And that benefit would probably carry over to certainly parts of your country. I'm not going to say anything more about bifacial modules, but if you do want any more information about it, send me an email and I'll give you, I've got a number of reports and other pieces of information. I work with a group in Eastern Canada who have a wind farm, and they've just installed a solar farm as well. And that solar farm, it has half conventional PV modules and half bifacial modules. And they did that deliberately, so they're going to do a comparison between the performance of the conventional PV modules and the newer bifacial modules. So, as I said, most of the information that's in the SAM database is just restatements of what you can get from the manufacturers' data sheets from their websites. There's a whole bunch of other stuff here. For example, the nominal operating cell temperature, 46 degrees. And when you do a PV analysis in SAM, the next thing you have to do is specify the inverter. And I've talked a little bit about inverter characteristics. So again, there's nothing special about this inverter. It's just one of the many that are there. You can see that it's sitting at around 96% efficiency for most of the voltage, the power output range. That's pretty impressive operating conditions. Then we come down to the last thing that I want to show you tonight, the system design. And this is where I would like you to do some experimentation for yourself. Okay, in this you can do a range of tilt angles and azimuth angles, and also you can look at the difference between a fixed system and a tracking system. So a single axis tracker means that it tracks in the azimuthal direction. So it follows the sun as it rises and sets. If it's a two-axis system, then it follows the sun as it varies with the season. But if you use SAM, it's very easy to look at how the value of the tilt angle and the value of the azimuth angle change the performance of the system. So you can come to this part of SAM in the system design bit and just vary those numbers and see what the output is. And basically all you do there, if we don't go into any details on shading, if you're interested in shading, you can follow it up with the literature in SAM, but we don't have time to do that. I simply go and simulate that. Okay, so you can see that for that particular site, we're looking at a very healthy capacity factor of about 22%. And so you can go back and say, change the tilt angle to 40 degrees and re-simulate. And you can see very little change to the capacity factor. And that's because, generally speaking, the power output of a PV module over the year does not change dramatically with the tilt angle. You have to go to very big differences. So they're the sort of things that you can do with SAM. The alternative, I mean, intellectually, the equations that you need to solve to do the same analysis yourself, they're not particularly difficult, but they're rather complicated. And one of the real values of software like SAM is that you just click on simulate and it does all that work for you. Okay, and just to show it again, you can do that. And if someone is very interested in SAM, maybe you can figure out how to get a solar data file for Novosibirsk into SAM, and we can do some simulations for your city. So it's not quite 10:30 by your time. I've finished what I want to talk about today. What I will talk about next week is, first of all, I'll talk about shading with the effect of shading on PV. And then for the remainder of the two sessions, I'll talk a little bit about storage and system integration. So I'll finish there and answer any questions if anybody has any questions. Okay, I think you are free to go.